So Martian is next. Introduce yourself. Yeah.
Yeah, hey guys, my name is Mars, 33 seconds. And I work with Nathan Kitts, and so this is our recent work. So one liner for this is we're able to do sensing from very sparse and random sensor measurements. We only need 3 sensors to measure fields that is like a very large field, no matter it's in a graphical structure or it's just a pixel space. We can do things pretty nicely. And we not just, in this newest work, we are not just able to do sensing, which is like a spatial space prediction, but we're also able to do the entire spatial temporal prediction. It's a pretty cool work, and it's currently under review at PNAS, and we are happy to talk to you guys. And yeah.
Thank you so much. Yeah. All right, Shante.
Hi everyone, I'm Mike. I'm actually an undergrad in Vikram's lab, and what my project has been is implementing a machine learning model for object detection, mainly for insects on our microrobots. So in our lab and in Ubicom lab, there's like a couple different microrobots that we've been working on. One of them is the Millimobile that you can see in the top right, and you can see this image on the leaf. It's about the size of a quarter penny. So all this talk about like kilowatt hours and stuff like that, our robot can operate on milliwatts. So we've been trying to come up with this eco-friendly way for sensor readings, tracking, etc. And we got some pretty cool results given the tiny compute constraints on device. So if you want to talk more about that, my poster's right up there. Thank you.
Thank you. 1 minute sharp. Thank you so much.
Hey everyone, my name's Hunter. I'm a PhD candidate in the Civil and Environmental Engineering Department. My poster is going to be on a landslide hazard assessment using the LandLab Earth Surface Modeling Library. Specifically, we focus on the 2023 Turkey-Syria earthquake and subsequent atmospheric river. I want to spend my time going over the 3 main outcomes of the study. First, we developed post-seismic landslide hazard maps at regional scales using global satellite data products with compound seismic and hydrologic drivers. Second, we analyze how the sequence of extreme events influences that hazard. And finally, we look into the potential for developing seasonal landslide outlooks using historic climate data for more proactive mapping in high-risk areas. Yeah, thank you.
Thanks so much.
Hi everyone, my name is Moses. I'm a first-year PhD student in the computer science department here. I'm going to talk a little bit about the work that I've started on, and the question that motivated this initially was how can we build and inform more sustainable fishing gear? And as computer scientists, we approach this problem, let's get a lot of data, let's analyze it. And the first issue we ran into is when we have a lot of videos of animals interacting in their environment, how do we collect data efficiently about their behavior? And current methods are constrained in a number of ways. Automatically annotating and quantifying animal behavior relies on species-specific methods that require large human annotated data sets. And this issue has guided my research in exploring methods for more species-agnostic video understanding of animals interacting with their behavior using foundation computer vision models and self-supervised learning to make these tools more useful to a broader topic. And this work is really important because it will help make some of the powerful tools that we have access to as computer scientists more accessible across the environmental science domain. Thanks.
Thanks so much. Nino, go see the poster. You.
Yeah. Hi everyone. This is Yu Ni. I'm a PhD student from the Earth and Space Science department working with marine. We know seismology is becoming increasingly a big data field with stations globally wide recording data that exist in petabytes. And researchers are motivated to use advanced computation tools and infrastructure to extract useful information from this massive ground motion recording. And in this experiment, we are collaborating with major data and computation facilities to run this machine learning cloud-native workflow that scan 1.3 petabytes of the continuous seismic data beginning from 2002 all the way until this year to extract earthquake phase arrivals. And at the end of this experiment, we are presenting this global scale seismic database, phase database with presently 4.3 billion pics globally wide. And we envision that this is going to be a crucial resources from the community to study earthquakes sequence and the seismic hazard assessment. And we also demonstrate the advantage of using advanced cloud computing infrastructure for high throughput seismic waveform analysis. So more to chat with the poster outside. Thank you.
Hi, I'm Hao Yu. So our work is more social and community-driven like work. I'm a student in interdisciplinary urban design planning at UW, and this poster is like a collective work by our lab, Urban Infrastructure Lab, Microsoft Research, and our collaborator, community collaborator in Georgia. So we are trying to build in community-owned renewable energy infrastructure. So we all know the concept of community solar is very fascinating, but it's like more like a business mode rather than a real community asset or something. So we start from the true model we envision for community solar or microgrids, and we frame it like collective action. So the success of such actions depends on other actions. So we work with the community directly, and we are trying to develop the financial and social-economic models of the system. And then we want to develop an AI-powered interactive platform for the stakeholder to see the cost or benefit and also the uncertainty under multiple scenarios, and also like a platform for stakeholders to negotiate. Yeah, thanks.
Thank you so much. Great.